Okay, we'll go ahead and record this. So for H2S, if we go back and do valence, we've got these coming in with 1, this coming in with 6. So we have 8 valence. If everybody was happy, then there would be 2 times 2 and 8 times 1, 4 and 8, 12. So they're going to be sharing 4 electrons. So 12 minus 8 equals 4 shared divided by 2 equals 2 bonds. And that's all good. And everybody can do this. So however we choose to put those. And I do this by default. We'll talk about that, why I do that more when we talk about molecular geometry. I'm sorry, I'm in the way. The thing that I'm seeing on just a few, and predominantly, I should get rid of this. Whoops. I'm seeing it when people are doing this. Get it right, Moser. I'm seeing people doing something like that for unshareds. Unshared pairs are always pairs. Unshared pairs are always pairs. They're always in twos. And the way to think about this is an orbital that's not being shared. And how many electrons can you have in an orbital? 2. So they're never solo. Yes, ma'am. So there were a few of you who I saw had some things like that. That would be wrong on a quiz. That would be incorrect. So for those of you who are sitting at like the 3 level, so yeah, you think you pretty much have this, but do you just feel like you need more practice? Okay. Couple things. There are some of these in your homework, right? And there are a few. Yeah, no, there are some in your homework. So what we're going to do is we're going to go ahead and start to talk. We're going to move on a little bit. I want to talk a little bit more about resonance because you didn't get a whole lot of that, and I want to practice some that are show resonance structures. And then we're going to start to talk about ionic compounds, and we're going to do that in the framework also of Lewis structures because I do want to kind of keep the thread of Lewis structures. Did I mention that I screwed up the order of operations? Every year, this year especially, I think. We've got another lab to do before we do the molecular geometry lab, so we're probably going to do that lab on Monday. I will have the lab packet for you tomorrow, and it's comparing the characteristics of ionic and covalent compounds. So we'll start that one on Monday, and then we'll get into molecular geometry, and then we'll do the molecular geometry lab. So, question? So let's kind of make a list of issues with Lewis structures. Like, this is the part I never get. Like, where do I put fill in the blank? So this is a huge one for, I think, probably a lot of people. Other specific issues that you can enumerate. Sabrina first.
How to line it up if it's like a C and then it branches up instead of like to the left or the right.
So like where to put stuff around the atom? Like where to put the bonds?
Yeah.
Okay. So you know how many bonds to put, it's just where the heck do I put them? Okay. Okay. Madison.
I'm confused like with the rules of it.
Okay.
Like I know carbon could be like bonded 3 times.
Okay.
But like one of the problems I got nitrogen and it needed 3 bonds.
Yes.
So I just
Okay. So what can bond how many times? Other specific questions? Yes, ma'am. Like polyatomic ions in general? Okay. Other ones? Okay. So let's spend some time. We'll do some examples with lots of unshared pairs, and we'll do some other stuff. So, okay, let's do some practice together. This is methyl bromide. It's an organic compound. So CH3Br. First step, figuring out valence. And you guys said you know how to do this. So we've got CHBr, 4 times 1, 1 times 3, 7 times 1, 4, 3, 7, 14. Okay, and octet. Carbon wants 8, hydrogen wants 2, bromine wants 8, times 1, times 3, times 1. So 8, 6, 8, 22? Yeah. So since they want 22, but they only have 14, they're going to have to share. And 14 minus 22, or I'm sorry, 22 minus 14 is 8 shared. So divided by 2, that means we're looking at 4 bonds. And how many unshared do we have? Well, we're sharing 8, but we have 14. So 14 minus 8, we have 6 unshared. Okay. So we know that what goes in the middle? Carbon. Carbon, carbon, carbon. So we're just going to arrange these on each side. I mean, the basic thing to think about in terms of where the bonds go is to remember that the nucleus of each one of these wants to be as far away from the other nucleuses as possible. So if you have 4 things attached to that central atom, they're going to be 1 off each side. And in this case, unshared pairs count too. If you have 3 things and 1 unshared pair attached, they're going to be 1 off each side. If you have 2 things and 2 unshared pairs, they're going to be 1 off each side. So really, you're kind of treating all of these as though there are 4 sides until we get into some of the really big weird ones, and we'll talk about those later. So we have 4 single bonds. Everything is happy. Now the question is, where do our unshared pairs go? Does carbon have room to take anything else? No. Carbon is satisfied in terms of octet, and that's the big thing to look at when you're looking at who should get those unshared pairs. Who's not yet satisfied in terms of octet? Yes, sir? Bromine. Right. So hydrogen can only take 2 electrons, and it's got 2, 2, 2. Carbon's got 2, 4, 6, 8. Let me get rid of my extra dots there. The only thing here that can take unshared pairs would be bromine. So that's our final structure. That's really what you're looking at when you figure out where the unshared pairs go, is who isn't satisfied yet for octet. And the number of bonds that something has formed will dictate how many unshared pairs they need. Yes, ma'am? I understand your question better now. It doesn't matter in that, remember, these are not real electrons, and bromine atoms do not have a Br stamped on them. So don't get too attached to the symbol that we're using to represent reality. You do have to put them in pairs. You can't, I'm going to mark it wrong if you do this, because those aren't pairs. I don't care how sloppy you are. Be a little bit neater. Those are not pairs. And we kind of treat each atom like it's got 4 sides, but the difference between, and oxygen is one that very often has 4 unshared. We tend to just put them on the opposite sides. The key being that those unshared pairs want to be as far away from one another as possible. They also want to be as far away as possible from whatever else is bonded to oxygen. So if oxygen is bonded to, well, Yeah, okay, fine, just leave it that way. If it's double bonded to carbon, you know, we can put the unshared pairs there. What very often chemists will do is this, because what that indicates is you have three things hooked to one thing. What's the farthest apart they can get? As if they were pointing out towards the corners of a triangle. So, and that gets more into the geometry of it. When we do the geometry lab, you'll understand this better. For now, we'll say that, you know, having all the unshared pairs correctly assigned to an atom and having the bonds correctly assigned to atoms is much more important than which side they go on. You know, some of that is just formality and it's convention, and it's not reality because, like I said, bromine atoms do not have a little BR stamped on them. It would be really cool if they did, but they do not. Let's do another one. F2O. So valence, O has 6, fluorine has 7 times 2, 6 plus 14, we have 20 valence. Octet, 8, 8 times 2, so 24. So shared, 24 minus 24, so 2 bonds. And how many unshared? Well, they're sharing 4. They have 20, so 20 minus 4, 16 unshared. This is a great one for this. Okay, so we know which one's least electronegative here? Oh, fluorine's the most electronegative thing there is. Fluorine never gets to be in the middle. This is like the younger sibling who says, I never get the whatever. Yeah, you're right, fluorine. You never get to be in the middle. Life's not fair. So oxygen is central. We have 2 bonds. So that's our basic structure right there. Now, to assign those 16 unshared electrons, we know that fluorine comes in with a whole, almost complete circle of unshared pairs. So we'll go ahead and stick those on there. 2, 4, 6, 2, 4, 6. So now we're up to 12. We still have 2 unshared pairs. Who is not satisfied from an octet perspective? Oxygen. And if you remember, oxygen came in with 2 lone pairs. So you're really just preserving that. Nothing has changed. That one probably wasn't a real tricky one, so probably not the best example. Okay. So the phosphate ion. We start off the same way we do with everything else. Oxygen and phosphorus. Oxygen has 6 valence electrons times 4. Phosphorus has, oh hey, there you go, 5. Times 1, 24, and 5 is 29, but we have a -3 charge. So this has 3 more or 3 less electrons? 3 more. So plus 3, we get 32 valence electrons for this. And if everybody had a full octet and was really happy, and I'm gonna do, you know, I sometimes do this cheater shortcut, and as you get better at this, you're welcome to do this too. Everything here wants 8, and I have 5 things, so 8 times 5. So 40 would be my octet number. You know, the place to be cautious about that, and the reason I don't show you that right off the bat is because you have to remember that hydrogen doesn't want 8, boron doesn't want 8, so you have to consider that. Okay, so 40 minus 32, we get 8 shared divided by 2, we get 4 bonds. And we have 32. We are sharing 8. So that's 24. Unshared. Okay, let me shrink all the math here. Yeah, I can hardly remember how I taught this before the Gooch math, because the math here makes it so much easier. It's amazing. I mean, it was always like, well, you just kind of have to do this. Well, you just kind of have to know. No, that's ridiculous. That's stupid. There are real answers for everything in science. We have numbers. We can assign them. Okay, so we have 4 bonds and we have 5 things. Phosphorus in the middle. 1, 2, 3, 4. 1, 2, 3, 4. Okay, well, that looks pretty good. Now, how many unshared electrons do we have? 24. So each of these oxygens came in, let's see, 2, 4, 6. Well, okay, you know, not to give away the punchline, but geez, you got 4 things. 24 divided by, 2, 4, 6, 8, 10, 12, 14, 16, 18. That's 24. Now, because it's an ion, we have to do that. The way that I used to teach, I don't even want to go there. I don't want to confuse you. I don't like to throw gasoline on a fire. Anyway, it's much easier this way because you know that there are this many unshared electrons. You're not worrying about, well, where did those come from? Where did they move from? It doesn't matter. It just doesn't matter. Don't worry about where they came from. Electrons are electrons. When Olivia gets shocked by her locker, the electrons that she transfers to the locker were hers for a while. Now they're the locker's. You can't own it. You can't own the electron. They move, they travel, they go. So don't worry about where they came from. Just worry about how many there are and whether they're shared or whether they're unshared. Okay, so that one's an ion. For those of you who had said, like, ions give me fits, did that help? Because you can just trust the math on the ions. That's all you have to do is trust Gooch. And he now, I think, is a stay-at-home dad. I think his wife works for NASA. And anyway, neat guy. I read his blog. He's got lots of good chemistry teaching stuff, even though he's not actively in a classroom right now. Okay, let's do my personal favorite. This is the nitrate ion. Nitrates are commonly found in cured meat products. Nitrates are found in gunpowder and fireworks. It's pretty ubiquitous. If you look at any kind of processed food, you're probably going to find some sodium nitrate or potassium nitrate. And they're both compounds that we use in the lab a lot. So, to draw the nitrate ion, let's do the Gooch math. Nitrogen comes in with 5, oxygen with 6 times 1 times 3, 5, 18, 23. And it's got a charge. So does it get 1 more or 1 less? 1 more. So plus 1, we have 24 valence. If everybody was happy here, so that's my valence. For octet, if every single atom here was happy, and there are 4 of them, we would have 32 octet. So 32 minus 24, we get 8 shared. Divided by 2, we get 4 bonds. And unshared, we have 24. They're sharing 8. So there are 16 Gesundheit unshared pairs. Okay, so the math is good, right? The math is straightforward. Need that moved. Or this. Is that better? I don't want to handle the... Okay, so straightforward. We've got the math. I'm going to shrink down the math. Is anybody starting to get a funny feeling about this one? Okay. What's giving you that funny feeling? Oh, 4 bonds, but only 3 oxygens. So we know nitrogen's in the middle because it's less electronegative. So we will start off, actually let me move all this up here. So nitrogen, oxygen, oxygen, oxygen. And I'm just doing that for now. For those of you who like, which side do the bonds go on? It doesn't matter. So if I hook everything together with single bonds, I still need one more bond. So what do? I put a double bond in. So now I have the nitrate molecule. What am I missing still? Unshared pairs and brackets. Yes. That's what we're going to talk about next. So how many unshared pairs do I have? I have 16 unshared electrons, I should say, not pairs. So I have 8 unshared pairs. So let's start out with this guy, this oxygen over here. 1, 2, 3, 4. Is that oxygen happy from an octet perspective? Yes. Stop right there. It's satisfied. Don't give it any more electrons. That oxygen, well, is the nitrogen in the center satisfied from an octet perspective? Yes. 2, 4, 6, 8. It's got 8. It feels surrounded by 8 electrons. That oxygen at the top, how many pairs would it need to feel satisfied from an octet perspective? 3. My top pair looks a little bit funky, but it is a pair, I swear. Okay, and so we've got 2, 4, 6, 8, 10. Wait, 2, 4, 6, 8, 10. So we need 6 more. Gee, how many unshared electrons does this oxygen need to feel satisfied? 6. Funny how that works out. 1, 2, 3, 4, 5, 6. Okay, so we bracket this bad boy. We put the charge there. Are we done? No. What's the problem? Prove to me that the double bond exists on that one. You can't. How do you know the double bond exists there? You don't. You have to draw what? You have to draw resonance. That's why I said this one's a big pain in the tuchus. So double-headed arrow, yet another set of brackets. And we have to draw that double bond in every place that it could potentially exist. What? Did somebody just say that?
Yeah, I did.
Okay. Are we done? No, one more. And nitrate is commonly the one where people run out of room and start doing really weird stuff, but that's okay. I'll draw it just a little bit bigger and then shrink it if I have to. Now we're done. And yes, you have to draw that whole stupid thing every time you draw the nitrate ion. And yes, your arrows have to be double-headed. What a dictatorial control freak. Seriously, lady, get over it. Sorry. It's just the way it is. In terms of where to draw those bonds, so I drew the nitrate this way, and it's fine if you're just talking about the Lewis structure. When we get into the geometry of it, the thing to remember is that those oxygens want to be as far apart from one another as possible. Let me shrink this to almost nothing. Let me move this up. So really what you would want to draw, if you were being as correct as possible, would be those oxygens forming kind of a triangle off of the central nitrogen, because, like I said, they want to be as far away from one another as possible. You know, for right now, we're not talking about geometry. We're not talking about what's called Vesper theory. That comes later in the chapter. So it's okay to draw it like this. But if you're, especially if you're moving on in chemistry and you're going to be doing chemistry in college, once we get to the geometry part, you'll want to pay attention to that. It matters from an electron repulsion, proton repulsion perspective. So you'll want to kind of catalog that. And when we do geometry, you'll have to know that this is going to form what's called a trigonal planar molecule, or ion in this case. Okay, questions. Let's get back and look at the list of things we need to check in on. So I think, did we cover where to put lone pairs? Okay, where to put the bonds? Did we cover that? Do you feel, whoever's question that was, you feel more comfortable with that? Okay. How many times can something bond? Do we feel more comfortable with that? That's, again, it's all about looking for octet satisfaction. So if it's not satisfied based on octet, then it can bond again. If it is satisfied, it should not bond again. We don't want to force any more electrons on it. Polyatomic ions, better, okay. All right, what we're going to do, having done this, I would recommend that you look at the Lewis structure practice in your homework. And tomorrow when you walk in, we'll have a FIP quiz on Lewis structures. It would have happened today had I been here yesterday, but I wasn't, so it didn't. So, other questions? You know what? No, I'm going to, hold on. We've got 11 minutes. Okay, so we've been talking about these polyatomic structure, or these covalently bound structures. These are what we usually show with Lewis diagrams, with Lewis structures. Ionic, things don't just bond covalently. We also have ionic bonds that occur. And we talked about the metaphor of, you know, standing shoulder to shoulder versus holding hands intertwined. In a covalent bond, they are holding hands. Their fingers are intertwined. They are physically interlaced. In ionic bonding, they're just side by side. But they are, an ionic compound is made of huge numbers of positive and negative ions. So I have my chunk of salt over here. And this is a chunk of halite from the mines underneath Lake Erie. It's really pretty. I need to get some hairspray on it so it quits picking up water. But this is made of huge numbers of positive and negative ions, all standing shoulder to shoulder, all very fiercely attracted to one another. That's kind of key. Most ionic compounds are crystalline solids in nature. So that salt is no exception. We've got some like copper chloride crystals in the back. They're really beautiful blue crystals. Like I keep threatening to dip one in lacquer and make a necklace out of it because they're gorgeous. They're these like cool crystal forms. If you've ever seen jewelry that's made out of crystals, amethyst crystals or quartz crystals, they tend to be really neat looking. And they've got definite geometry. We'll get into crystalline solids a little bit later in the year. So we have these ionic compounds, and we can actually show them bonding using Lewis structures too. So if we want to show the transfer of electrons and how we form an ion, and we want to show what an ionic compound looks like, remember they're not sharing electrons, so we're not drawing these things interlaced, they're not holding hands, they're side by side. So the old classic example is sodium. And we'll do chlorine because everybody likes sodium chloride. It's tasty and delicious. So we know that sodium, to look like a noble gas, would shed that one electron, and sodium does this readily, forms a positive ion. When we show sodium having shed that electron, of course we show brackets because sodium is a what now? It's now an ion. So we have to show its charge. So this is a sodium atom. This is a sodium ion. This is a chlorine atom. That is a chloride ion. If we want to show those two forming a compound, remember, they're not holding hands, they're just standing side by side, and that's pretty much literally what we show. There's sodium chloride. They are not sharing any electrons. They don't play that way. Sodium doesn't love electrons enough. Chlorine loves them too much. So sodium has given up its electron. But that raises a fantastic point. So typically, for positive ions, how many valence electrons are you going to be showing? So for positive ions, how many valence electrons will you be showing? Here is the magnesium ion, the magnesium atom. When magnesium forms the ion that it would like to form, how many valence electrons will it be showing? None. The positives tend to give up because they tend to be things that have 1, 2, or 3 valence electrons. They tend to just give them up. So the Lewis dot diagram for positive ions tends to look like that. It doesn't show any valence electrons. What about nitrogen? Because nitrogen does form a ion. So if nitrogen forms the ion that it wants and gets all the valence electrons that it wants, it forms a 3 minus. How many valence electrons would be shown in this? 8. The negative electrons tend, when we do a Lewis dot structure for the negative electrons, they tend to show all 8 because they basically grab electrons until they have a full complement. And nitrogen's one that it bonds covalently very often. It shows up in a lot of covalent compounds, but it also does form ions. So we do have nitrite ions. Good question. All right, this is the very last thing, and we'll stop with this. We'll go into this a little bit more tomorrow after your Lewis structure quiz. So we said ionic compounds form these beautiful crystalline structures. They're called crystalline solids. They actually form a lattice, and there is a fantastic image of a crystal lattice on page 177 in your book. I'll take a picture and insert it here. So they form, it really looks like a scaffold with little beach balls on it. They form these beautiful lattices, and the whole thing is this very, we'll pick it up tomorrow. Lewis structure quiz tomorrow when you walk in.